Welcome. This is the fourth video in the series on Principles of Radiographic Exposure 2. In this video, we will learn about digital radiography. In the last video, we learned about CR. And if you haven't watched it, I recommend you do it now as there are many similarities between CR and DR. So, DR, students think it's scary, but it's not really. If you have read your text or are watching this video for a review, you may be confused with DR at this point. I think in text they don't break down the components enough that can give students a better and or easier understanding of digital radiography and the processes which make it possible. The only difficult part that is there is with the technology, maybe, and that it's hidden and that we never actually see any of it happening. As with CR or film, you can see the image plate, the PSP. You can take it out, you can see it, and you understand the reader and how it's reading it and all that kind of stuff. And with film, obviously that was much more hands-on back in the day. So with DR, everything's happening electronically, and it's happening inside a device that we call the image plate, the detector, and we're not really sure. So that's some of the difficulties that we may have. But with that in mind, let's get started. We will start with the background on how digital radiography became to be. From the discovery of medical imaging, the film screen process was the method of image capture. So this is with old films that you would hang up. In 1981, the first digital imaging system, which is CR, was introduced by Fuji. The system used cassettes that stored an image on a plate that received the X-rays and stored the anatomical information as excited electron states. The cassette was then processed by the reader, computer-based processing occurred, and the final image was displayed on a monitor for interpretation and to be sent off. Well, the CR process had inefficient X-ray detection, low spatial resolution, and multiple steps required by technologists. With miniaturization of electronic components through the 1970s, 80s, and 90s, it became possible to make radiology detector elements small enough to be below human visible spatial resolution. So the technology had to come along such that each element of the digital detector is smaller than what our eyes can distinguish, is what that means. This allowed fully electronic X-ray detectors to be viable, a viable means of medical imaging. The first DR systems were revealed in 1995. We'll go ahead and we'll introduce some terms that will be used for during our lesson in DR. The first one is DEL. The DEL is a detector element that is a square that receives the information contained in the X-ray. All the DELs of the detector make a grid which relates to a matrix. So all the DELs are, you could say, is a matrix of these elements, and each one of these is what has to be smaller. Okay, and we'll learn about the components inside each one, but each one has to be smaller than what our eyes could distinguish before DR became viable. A dexel, you may see that term in books that may be used, just so you know, is a DEL with the exposure information collected in it. So dexel is kind of like pixel in that regard, and the DEL is the physical element on the detector. The dexel is when it is the information that's contained on each one. Okay, and just like the matrix can be made of, on a display, can be made of pixels, the matrix of the image information on the detector is made up of all the dexels. Okay, so that's kind of where that comes from, the dexel. So amorphous is a solid that has characteristic anatomical arrangement more like a liquid. So amorphous, this means something that's solid but has characteristics of a liquid. A phosphor is a substance that exhibits luminescence, and luminescence is typically to give off light, but it can be to give off any kind of energy. It's typically associated with light, as far as I know, of phosphor. Scintillation is a small flash of visible light or ultraviolet light emitted by fluorescence in a phosphor when struck by a charged particle or high energy photon. So a phosphor is a physical thing. Scintillation is that flash of light. So when something is a scintillator, it could, like phosphor, scintillator, it could be, you could be referring to the physical object then, but scintillation is the process of the light being emitted from the phosphor. And notice by a charged particle of high energy or high energy photon. So it could be a particle, a neutron, or electron, or something like that. But what's useful to us is high energy photon, and a high energy photon is an X-rays are very high energy on the electromagnetic spectrum. Photodiode is a semiconductor diode sensitive to photon radiation. So photon, in this sense, can mean anywhere on the spectrum. Photo just refers to electromagnetic. It's typically associated with light. We'll get started with the image receptor. So the image receptor. This is what it could look like here. The image receptor can also be called the detector, a DR, a DL panel, a cassette. All these terms could be used. Okay, cassette's kind of an old term for like associated with film, but I still use it, cassette, as a term. In the text, we use all these terms, so I'll use them all as that's how they are in the field. It is constructed of a strong outer material, usually carbon fiber, that protects the inner electrons from damage and moisture. This isn't like a printed on carbon fiber either, it's actually carbon fiber. Detectors can be damaged from dropping, bumping, flexing in high pressure situations, and this can be distributed over the pressure can be distributed over the face of the detector or at a single point. And it is usually from the patient's weight being on it. Detectors may have bumpers, fluid resilient seals, and other features to protect it from these damages. The electronics inside are very expensive and complex, and we want to protect it. And we want to be careful with the detectors. Back in the day where we had film or CR, you had multiple cassettes. Here you only have the one that you're constantly using. A detector is made with intricate technologies and is a significant cost to purchase, as we just said. The radiographers take precautions to protect the IR from abuse and potential damage. If damaged, the detector contains sensors that will alert the technologist of the need for calibration tests and to run to check for damages, and will determine if it's still operational. So if it is dropped, a lot of times the system will come up with a message. The message will explain how to run. It's usually just taking a series of x-rays at a certain thing, and it may even enter it into it for you, into the process for you. If you say, okay, I want to run the test now, it'll come up with the technique it wants to use, how far away to be. It may have pictures and diagrams to do, but run the test. The information that's being received back and forth from the detector to the computer, it will determine if the detector is still within specs, if it's okay to be used on patients to produce the images that we need, and if it's still operational. If significant damage has occurred, though, the manufacturer will analyze the panel as to the cause and degree of damage to the panel. And it may be able to be repaired or it may not, but that's not for us important for us. The image receptor. Image receptors have a capture element, a coupling element, and a collection element. These elements can be made of different compounds and technologies, and of course we'll talk about all these. The image receptor can be of an indirect or direct type. So there's two different types of image detector, and it can use different types of technology. Okay, but for the most part, each one has a capture element, coupling element, and a collection element. Some don't have a coupling element, and we'll talk about that. Direct conversion is X-ray photons absorbed by the coating material in the capture element and immediately converted into an electrical signal. Indirect conversion is a two-step process. X-ray photons are converted to light, and then the light photons are converted to an electrical signal. So indirect, there's another step involved here. Okay, so it's very easy. So direct, the X-rays become electricity. Okay, and then indirect, it becomes light first, and then it becomes electricity. So these two terms are very obvious when you think about which one's which. Now let's go ahead and talk about the detector elements. So here we see a diagram of the detector elements. We have the capture element here, okay, and this is where the X-rays are coming into. There's the secondary photons, and secondary photons is light in this case. This would be like a phosphor. Scintillation occurs, and it will produce light. There's the coupling elements, which take the light into the collecting elements. It could be of two different types. Some, they don't have this coupling step, okay, and that's of course with a direct type, but all the different manufacturers could make theirs in different ways. Okay, there's different phosphors, there's different technologies that they put into it. Okay, we will start now by talking about the capture element. Capture element is the first part of the detector that the X-rays interact with. In CR, this is the PSP. So we would say that the capture element in CR is the PSP. Photostimulable plate. In DR, the element may be made of sodium iodine, cesium iodine, gadolinium oxysulfide, or amorphous silicon or amorphous cesium. Okay, I think there should be an in there. The capture element converts the analog X-rays to light in indirect detectors and to an electrical signal in direct detectors. So the capture element receives the X-ray, makes sense. Indirect goes to light, as we learned, and in direct it's going to go to a electronic signal through this capture element. There's also coupling elements, and we have the diagram here. So we talked about the capture element. Now we're going to talk about the coupling elements. Coupling element is that which transfers the X-ray generated signal to the collection element. The coupling elements may be a lens, which could be like here, which is, we would say, is more used in CR, in the CR reader, but it could also be in cassettes. Some texts say different things on this, and some may be an older technology or maybe like a newer technology. I'm not quite sure which way the lens goes. Or fiber optics, which is more often the case, I believe. So fiber optics are just thin strands of glass, okay? But a light particle, well, it's particle wave, particle duality, but a light beam, we'll say, gets in the fiber optic and it can't escape it, okay? They're made in certain ways, all right? And so it travels down it, okay? And you can see from this that you'll capture it here and it'll send it to the collecting element right down to the line. Okay, so this is a way of kind of funneling or coupling, kind of putting everything together, right? The signal to the collection element. All right, so it keeps it in the right spot as much as possible is really the purpose of it. The fiber optic assembly is employed in indirect capture, and typically like a contact layer could be considered the coupling element in direct radiology. The fiber optics are utilized to focus the light produced by scintillation from the capture element, as we said. Collection element, this one doesn't have the animation, but it's fine, can be called, is that which collects all the signals. Okay, so this is collecting all the signals, and it could be the electronic symbol or it could be the light signal. Okay, it may be like a photodiode, which we learned about in SEER, a charge couple device, which a photodiode may be in some DR technologies too, from what I read from text. Charge coupling device, which would be CCD. It could be CMOS, which are two different technologies, or a thin film transistor, which is called TFT. And this uses amorphous silicon, and it should be amorphous selenium. Okay, amorphous selenium. Now let's go ahead and explore what makes up the collection elements a bit more. We will explore how they and also here we'll explore how the capture elements come into play by talking about TFTs, which is thin film transistors. And so far we've talked about coupling elements, collecting elements, and capture elements, and what they are and what they're made of. And now we'll go ahead and we'll start putting some things together with the TFTs. This is a diagram here of direct versus indirect. So as we said before, the X-rays come in, light, it gets converted to light, okay, and we know this phosphor would be just the capture element, right? Then there's the collecting element would be in here, okay, which is directing the light, and then there's the collection element down here, okay, and this would be considered the collection element down here, which is collecting the charges, okay, and each one of these right here could be considered a del, okay, each one of these is a del, and it would be on a matrix, and there'll be millions of these, okay, throughout the detector. All right, in direct, X-rays come in, typically amorphous selenium, right, or silicon, and it creates a charge. Okay, so it creates an electrical signal, and that becomes captured down here. All right, and there you can see there's different dells down here. There would be like 1, 2, 3 in this setup here. Okay, so that's another rundown and a picture of direct versus indirect. Let's talk about thin film transistors now, which we call TFTs. Transistors, we can see transistors right here, and we learn that they just act like a switch. There's a source, a drain, and a gate, and depending on what the input is, they will either switch on or off, and they will output that signal. TFTs, however, are a distinct class of metal oxide semiconductor field effect transistor, which is MOSFETs. TFTs are electrical components layered onto a glass substrate that includes the readout, the capacitor, and the capture elements, which could be amorphous selenium or silicon. TFTs are used in flat panel displays, laptops, cell phones, so TFTs are everywhere. And you may not have even realized the technology that allows flat panel displays and laptops and cell phones is TFT technology. So TFTs are incredibly thin. Okay, they're not bulky like these. The first thin film transistors were flat panel amorphous silicon and amorphous cerium detectors were introduced in 1995. So the first TFTs came out in 1995, and we can see a picture of them here. So there's the capture element right here. Once it's captured, it will go to the storage element, which is a capacitor. And then there's the readout electronics would be in here too. And then there's also the thin film transistor right here. And and this will just act like a switch for when the information needs to be read out. So let's talk about the direct conversion type TFT. The detector has a radiation conversion material, typically the amorphous selenium or silicon, and it's about 500 micrometers thick. So it's very, very thin. It's 0.5 of a millimeter. It's 500 micrometers. This material absorbs X-rays and converts them to electrons, and the electrons are stored in the capacitor. Okay, so in direct conversion, as we learned, the X-rays directly become a signal in direct conversion. It doesn't have the light step like indirect. And the TFTs in the diodes act like a switch, and it sends the charges to the image processor. Okay. There are storage capacitors in each row, and the information stored in, and it's discharged into the data columns and the readout columns with dedicated electronics. More than 1 million diodes can be read out and converted into a digital image in less than 1 second. So that's pretty phenomenal that 1 million diodes plus on the detector can all be read out and converted into the digital image in less than a second and be displayed by the display device of the X-ray room. So this may not be the final image, it may be the raw image, okay? And there's other image processing techniques that will happen to produce the final image, and we'll learn about those in the later videos of this series. Image, okay? The initial look of the image. So TFT, so this is just another view of it here, okay? There's a TFT switch, and there's the charge collector, okay? And there's a storage capacitor in here somewhere too, right? And so the X-rays come in, okay? It hits this layer here. There's the detector matrix here. All this can get read out along the data lines, okay? And then there's timing controls, there's address buses, there's all kinds of things, and then it gets read out to the system, okay? And you see here that the system can go back and forth, right? So the system, the operator's computer and everything, right? It's sending data back and forth too, okay? Calibration data and other kinds of things during this process. Indirect conversion for TFT, we'll talk about the gadolinium oxysulfide first. Indirect conversion changes the X-ray photons to light, and then the light is converted back to an electrical signal. This is indirect. I hope we're getting the difference between indirect and direct at this point. Phosphorus, such as gadolinium oxysulfide, made from small crystals bound together in an unlayered structure, is utilized. The crystalline structure has air pockets that can allow light to escape. Okay, so this gadolinium oxysulfide could be a little less than ideal. This reduces the efficiency and lowers the spatial resolution. Gadolinium oxysulfide was primarily used in applications where rugged detectors were needed, and it was more kind of in the early days, all right? But this is still a capture element that that we need to know, because it could be still in use in certain applications. And with some of these phosphors, their manufacturers are getting better, okay? Even though it's the same phosphor, they're getting better at manufacturing it. So this kind of air pocket light leak that happens, right? And remember, the light at this point is the signal, okay? So we don't want that to leak. We need that to get to the collection elements, so we can read it and create an image. This reduces the efficiency. Okay, but they're getting better. That was my point with manufacturing some of these things, so it's still learned about. So indirect conversion also with TFTs technology. You can use CSL. So the cesium iodine is the most popular type of scintillator phosphor. It is made by growing very thin crystal needles, about 5 to 10 micrometers in thickness. Okay, so these are little needles, so when the light goes down, it's already in the channel of this 5 to 10 micrometers, right? And then when it goes to the collection with the coupling element, it travels these channels much better. So this is why cesium iodine is much more commonly used. These crystals work as light directing tubes, as we talked about. This allows the greater detection of X-rays, higher DEQ than gallium oxysulfide, because there is almost no light spread. The spatial resolution is higher. Okay, so something that can degrade spatial resolution is where the signal is going, is where the signal should be ending up in one area, but it's going to another area, right? So it's kind of fogging a different area, in this case, it would be a different del. It's getting information that it shouldn't be receiving. So with this process of having the very thin tubes, crystalline needles, right, it prevents this greatly. Okay, we can actually see here the crystal, and then we can see it's scintillating. Okay, so this is being hit with some kind of energy. Okay, either a stream of particles or X-rays, high energy photons, right? And it's actually, you can actually see the light that it's emitting. All right. Early on, cesium iodine detectors could only be used in fixed applications. So this is why the gallium oxysulfide was used especially more early on, according to texts, is because the cesium iodine can only be used like in a fixed application. So this would be like a room setup where the image plate does not come out. Okay, it's part of the bucky. All right, and it was usually a C-arm kind of setup. All right, but it would be a room size kind of C-arm. Okay, where there's fixed distances and everything. All right, so that's what this means. But because of advances in the materials, in both can be used in potable detectors now. So both these materials are advancing. They're and they're both utilized. Okay. So we'll go ahead and we'll talk about flat panel array, which is also referred to as active matrix array. These terms will come up. So the way a flat panel array is designed, the functions is complex. However, the design is quite simple. There is a sensing component, okay, which is here, the X-ray converter layer, and a switching component, which is a TFT, switching, right, transistors. There are two switching components, a diode switch and then the TFT in here. The sensing components depends on the type of absorbing material and the vendor's choice of absorbing material. Okay, so depending on what type of material they have here, this will change. Okay, and it depends what the manufacturers want to make. The active matrix array, flat panel arrays, these kind of can more refer to where it's energized. Okay, where the electronics in here are energized from a source when it's taking the picture. Some of the other ones, they aren't energized. Okay, so there's not actually energy going through it. It's kind of nitpicky electronic stuff here, but just so you have an idea of these terms. And over there. Okay, so now we're talking about the collection elements a bit more. We already talked about TFT's pretty good amount, which is one of the collection elements, right? But here we'll talk about charge couple devices, which is CCDs, or CMOS technology, which is complementary metal oxide semiconductor, right? And these are only going to be indirect capture type. Okay, so where the TFT you can have direct or indirect captures. This is only direct. This is only indirect capture. So we're talking about charge couple devices. CDCs were developed in the 70s, the 1970s. So Y2K compliant, 1970s. It's a light sensing element for digital cameras. Okay, it's the most common thing. So in your phone, you have a CCD right there. Okay, so there's thin film transistors in displays. All right, there's CDCs and cameras. So these technologies aren't so foreign. Okay, so to say. All right, they can just be applied to radiology in different ways. Okay, and we can utilize that technology that was maybe developed for other things, and we can use them to do our digital imaging process. Okay, so it's just a light sensing element for digital cameras, and the light sensing part should clue us in that it is going to be indirect. Okay, because we need light, we can't sense the x-rays, we need the x-rays to be converted to light. Okay, so this is what is a CCD? Okay, and this is actually a view of it right here, so this is very good. Okay, so at the back of the camera, this is a SLR type camera, and at the back of it here, there's a CCD. Okay, charged couple device, and this is what is actually picking up in digital applications for image taking. Okay, this is what is actually picking up the light in digital cameras, and all we're doing, we're just adding much more complexity and much more accuracy, because we need to be much more accurate in medical applications, and we're just adding an extra layer by starting with x-rays instead of light, but we're making it light. Okay, so CCDs, a charged couple devices capture element, can be made of the cesium iodine or gallium oxysulfide, which is just the phosphor. A photosensitive receptor, an electron is embedded into the substrate material on a silicon chip. Make up CCD. So silicon is it's really just kind of sand. People say, okay, it's in sand. So but it's a semiconductor. Okay, so this is a semiconductor. Okay, so there's a silicon chip, and then the photosensitive receptors and electronics are embedded into the substrate, into the silicon. Okay, and that's what makes a CCD. Light from the scintillator, okay, strikes the detector, and an electron hole pair is created. So this sounds kind of complex here, but it just means that there's energy, right? When it hits this p-type, there's p-type, n-type, okay? But when it hits this, when the energy hits a atom inside of here, it will energize, right, the atom. It will respond by releasing an electron, and then there's what we call hole. So in the electron, in the shells, okay, of the atom, now it's missing an electron. Okay, so that's what we call a hole. There should be an electron there. There's not. Okay, and now there's an electron. This electron then becomes the electrical charge. Okay, more free electrons just come in. All right, and these free electrons is what creates a voltage. Okay, moving electrons is like amperage. The difference between two potentials, okay, where there's a negative charge and just a neutral charge, or even maybe a positive charge, okay, is voltage. So this is a V right here. So this is detecting a voltage, and that can be detected, and that can be interpreted as a signal of an image, okay, as a digital X-ray image. Okay, there you go. The electrons are read out to form an image, right? So that's the very basics of that technology there. Okay, energy comes in, creates an electron hole pair, and then that is read out. Okay, the electrons are essentially just read out as a signal. CCD, we'll talk about 3 advantages of it. There's the sensitivity, dynamic range, and size. So sensitivity can detect very low levels of visible light, important for low patient dose, so we can use less radiation because we don't need so much light. with this technology, right? So we can use less radiation and deliver a lower dose dynamic range, okay? The ability to respond to a wide range of light intensities. So the light that's coming out can be, intensities would be like color, right? Because the different light waves have different wavelengths, okay? That's what makes them different colors, right? Different wavelengths are different energies of light, right? So it can respond to a wide range of light intensity, so that's a plus for CCDs. And the size the CCD is small, approximately 1 to 2 centimeters, but pixel can be about 100 micrometers, okay? And as we learned before, that the human eye can only see down to about 200, it says, okay? Typical. So this is below the threshold of human vision that we can make it, and we can use it as a pixel or a Dell element, okay, that will eventually through many processes become a pixel on a display, and we can't tell the difference, okay, in the resolution. Let's talk about noise with CCDs though. So there's some disadvantage with CCDs, and that's the noise. Noise, static noise, current noise, and amplification noise. So static noise is created when a lack of light from the scintillator due to too few X-rays striking the scintillator. Okay, so this is just when you don't use enough technique, perhaps for whatever reason, or there's not an or there's some kind of other thing in the way. Maybe they have prosthesis and things, okay, so all that metal is absorbing a lot of the X-rays in that area, so it's having a hard time, the CCD will have a hard time with that low light situation, okay, low signal really, right, but the light. Current noise occurs when the CCD chip operates without radiation stimulation due to high temperatures, okay, so if it gets hot, okay, if the detector gets hot, so CCD chips are much more sensitive, okay, to this kind of thing. Amplification noise. So amplification noise is common in digital systems, and software can be used to correct it. All right, because the manufacturing process is so complex, there is no CCDs without amplification noise. Okay, so the signal is going to be amplified, and there's going to be a noise involved with that. That's all that this is saying. Okay. Let's move on to CMOS. So CMOS technology, as we learned, is the complementary metal oxide, okay? And a little more complex electronics stuff here. This is, there's P and N type, okay? And they're complementary transistors, all right? When one is powered, okay, it will produce a 1, but the other one will produce a 0, okay? So they can work together in different ways. And this is how we make electronic and computer chips and things today with CMOS technology, okay, different transistors. But complementary metal oxide semiconductors systems use a scintillator, okay, that when struck with X-rays convert them into light. So that would make them what type? Indirect, okay. Each Dell has its own amplifier when is switched on and off by the circuitry within the Dell, converting the light into electrical, which is, okay, switched on and off by the circuitry within the Dell, converting the light to electrical charges. Okay, so each Dell has its own amplifier in this technology. Okay, I guess that was all. So here's a quick look at each of the two technologies here. So we saw that in the CCD, charge coupled device, it was all shiny, right? It was very shiny, it was kind of glassy like. So this is a representation of that, okay? The signal gets received here, it gets stored for a second, and it gets read out, okay? And it gets amplified. This is like an op amp, okay? It's an amplifier. So in the CMOS technology, each one has its own amplifier, okay? But the point is that both of them, in all these technologies of the collecting elements, right? They convert the photon energy to electron. Okay, and electrons is just electricity essentially, right? And complex, kind of in the things that handle complex electricity and can change what they do with them, we call electronics. Okay, so this is all kind of electronics here, right? Inside each one. Let's go ahead and compare between the CCD and CMOS. CMOS is more susceptible to noise. Light sensitivity of CMOS is lower than CCD. CMOS is inexpensive to manufacture. Okay, so CCD is a more expensive manufacturing process. CMOS chips tend to have a lower quality and lower resolution than CCD for the most part. Both CMOS and CCD, though, provide excellent image capture abilities. Each have their strengths unique to applications, and neither is really superior to the other, okay? Even though these two technologies, there's different attributes about them, okay? And they're the manufacturer of the image receptors, they'll use one or the other in different ways, okay, depending on how they're making the detector, how they think it's going to be used, okay, and things like that. All right, and again, to go back to the beginning of the video, all this stuff is kind of hidden from us, right? So it's kind of like we may not know which type of technology is specifically used inside the detectors that we're using every day, that we're doing hundreds of x-rays with, right? But there are trade-offs between any technology that's being used. And the CCD is more difficult to integrate with the automatic exposure controls. Okay, so to have the CCD, a panel with CCD in it, it's more difficult to integrate with this, okay, and it's less accurate according to what I read too. Okay, it can have issues with the automatic exposure control getting the exposure to the point. Okay, so it may overcorrect and expose more than it actually needs to. It may expose a little less at times. Okay, so with the automatic exposure control, so this is to me an issue with CCDs. Okay. We have covered the elements that make up an image receptor, direct and indirect types. Now let's talk about a concept called the fill factor. The fill factor of a detector refers to the sensing area compared to the non-sensing area. It is expressed as a percentage, with 100 being the entire area of the imaging plate can sense photon energy. The fill factor has a direct relationship with both the spatial resolution and the contrast resolution. A detector with a higher fill factor will yield higher spatial and contrast resolution. So, and that's what we want, of course. We want higher spatial, higher contrast resolution. So we want a higher fill factor. The smaller the del, the higher the pixel pitch of the image will be. We want a high pixel pitch. The smaller the del, the lower the fill factor will be. Therefore, there is a trade-off, and most systems currently have the smallest dels possible. So the trade-off is between, if you make the dels smaller, right, the pixel pitch will be higher, but the fill factor will be lower. So in a lower fill factor will yield a lower spatial resolution and contrast resolution. This is due to the electronics taking up a higher percentage of space. The smaller the del gets, the electronics aren't going to get any smaller than what they already are if the del gets smaller. Therefore, the fill factor, the ratio of the sensing area to the electronics, is going to be much lower. We'll go ahead, we'll talk about some artifacts in DR. All right. For a more complete artifacts lesson on the QA playlist, there's a artifacts, and I believe it's the third video. There's an artifacts video, okay, and we'll talk about a bit more about artifacts in DR. But here, the loss of misrepresentation of image information is an artifact. It can be caused by damage, dust, scratches, static discharge, chemical corrosion, or interaction between materials inside the detector, okay? Or it could be an external thing, it could be coming from the outside, okay? That can cause an issue, okay? And some of the things that could be coming from the outside is like radiation from another source, okay? Could mess up and misrepresent the image in different ways, right? Noise, of course, is always there. So the biggest source of noise is scatter radiation, we say, in the image formation. But beyond that, there's also like electrical noises. Okay, we talked about the amplification noises that are always going to be there. Okay. And other sources, right? It's always noise can be an artifact. Misrepresentation of the image by the divergence of the light, okay, where the coupling element, the capture element, all these things, the light and the indirect style can converge or can diverge, go off in different directions than what it needs to be. So the X-rays through the capture, okay, so it gets misrepresented, okay, so it'll be the charge will be put in a different del than what it needs to be, right? And this can happen, this happens all the time, but if it happens to such a degree, the image isn't going to be displayed correctly, right? A del being in an always on or off state, okay, so the transistor inside or the capacitor or something, it didn't discharge properly, okay, one time, so it's going to read, always going to read as it being on, even though it's actually not, okay? And a lot of these things, or some of these things can be fixed with turning it off, okay? So sometimes it's good to turn off the detector if nothing's going on, if you're able to. Just leave it off for a couple minutes, let all the charges discharge, okay? We call it like leak out, right? From all the capacitors and all those things, and it can fix some of these things, okay? But there may be something else going on where it's always on, okay? Not just something so basic. A dead pixel is where the del is not functioning at all for whatever reason, okay? Something in the wiring inside, something with the transistor inside, something with this, and it could be all kinds of things, right? But this is called a dead pixel where the del, the element itself, is not functioning. As the detector ages, the number of dead pixels increases, okay? Manufacturers make efforts to maintain less than 0.1 to 0.2% of defective pixels, right? So there can be a certain amount of dead pixels on a detector, and you can never tell, okay? Because they're so small, all right? And they're processing information and everything. It's going to fill in that pixel with a process called interpolation. Okay, we'll learn more about these things in upcoming videos, all right? Image processing techniques, okay? Things that happen on that side, okay, after the information is sent from the detector, right? But interpolation is something that can fill in the dead pixel, okay, on the, so when it's displayed, we can't even tell, all right? That there is something physically wrong with the detector. The DR process, let's go ahead and break down the DR process, okay? So we've talked about the technologies, we talked about TFTs, we talked about CMOS, CCD, we talked about which is the collection element, we talked about what coupling elements are, we talked about what the capture elements are, right? And we talked about direct, indirect technologies, flat panels, okay? So that's all the basis of DR right there, okay? The technology is complex, okay? To design these things is very complex. To make them work extremely accurately is complex, and the size of them, okay? It's small, and how many there are and everything, get it all to work together and read out, okay? But for our purposes, okay, that's all we need to be aware of, right? There's the different technologies, okay? It's all hidden from us, so we don't really ever see it. but the manufacturers use different technologies, okay, as they see fit. The DR process. X-rays are produced at the anode of the tube. Okay. If you need a review on these elements, I highly encourage you to check out the video, the playlist, Principles of Radiographic Exposure 1. Okay, that will have all this information and much more details on how it occurs with these points here. Okay, the X-rays travel through a medium, which will be the air, okay, at the one point, and then it hopefully will be directed at the patient, right? We say so, and it will go through the patient. The primary beam hopefully is pointing at the patient with the detector in line with it, right? With the image plate in line with it. From that, the beam will come out. It will be the remnant beam, okay? And that will interact with the detector, okay? That will interact with the image plate behind it. The X-ray photons are either converted to light in the indirect or they're not, okay? In the direct style. It's not that complicated. So we'll continue and we'll talk about the capture element is made from the sodium iodine, cesium iodine, gadolinium oxysulfide, depending on the application, or it could be the amorphous silicon or selenium. They convert the energy of the incoming electron to a different form, and this is either going to be light when it's indirect, or it's going to be an electrical charge when it's the direct type. The coupling element is made from fiber optics, a lens or contact layer. They take the light or charge and guides it to the capture element. So not all the detectors are going to have something that's maybe considered a coupling element, but the indirect ones, when they convert it to light, they especially do. They have fiber optics or a lens, okay, to guide the light to the collection elements, which are made of TFTs, photodiodes, capacitors, diodes, CCDs. They could be photoconductors, CMOS, and other electrodes. So there's all kinds of things in there too, right? Depending on what technology the manufacturer uses. The stored data is then read out through the data lines where it is amplified and transmitted to the computer for image processing. The address driver controls the sequence in which the data is dumped. This registers where each data point is located in the matrix of all the dexels. Okay, so it keeps the information in proper places, and when it's read out to the computer, the computer knows this is the order it receives it in, so this is where it needs to process it and put it in what's going to be the final matrix of the image. Okay, there's many different matrices through the different steps of acquiring a radiographic image. And we can see here, each one of these would be like the Dell in this case, and each one of these will make a matrix, a physical matrix inside of the detector. Okay, and then once the data needs to be dumped, as it says, it needs to be read out. The data lines here, it will dump it. The address, it says decoded, but the address driver control keeps track of everything, okay? And it goes out through data bus and other electronics, and it gets sent to the computer. Here we have a breakdown, and we have the next couple slides, we have a breakdown of the different technologies used, okay? So we have the detector technology, we have CR, CCD, CMOS based, we have the indirect, direct, okay? And there's this electrostatic, okay, which is just a different classification of things. But it's here because the word may come up, okay, even though we didn't talk about it at all, right? So the CR, so there's the PLS phosphor, okay, which is typically the capture element, okay, the PSP, right? But it's the photostimulable luminescence, right? So it gets energized, it releases light through a light guide, and then there's a photomultiplier tube on the other side, okay, and it digitizes the signal, okay? This is how the CR worked that we learned about in the last video. There's a CCD and a CMOS based, okay? This cesium iodine, gallium oxysulfide. Okay, it could be lens. Here it is again, or fiber optic taper. Okay, and then there's CCD or CMOS, whatever the collection element is. Okay, the same thing here. There could be a contact layer. Okay, in the indirect. All right. According to this, okay, and then there's a photodiode, okay, which takes the light, converts it to electricity, or a TFT array, or a combination of both, right? Which this says or, so this is probably a combination of both right here. The direct, okay, there is no coupling element, right? Some say it's that this could be a contact layer too, but there's the amorphous cilium, okay, and then there's a TFT array, okay, in the direct. There is no converted to light, so we don't need this, right? And you can see the picture down here, the secondary energy carriers, whatever that happens to be, if it's the electrons or if it's light, okay? This is another look at it, digital radiography, okay? CR is considered digital radiography because it is a digital signal. It's not an analog signal like film is, right? So, so it's here, okay? And this is that. There's also the indirect, okay? And that uses the fiber optics, okay? We can have this with the contact layer, as we talked about, and the TFTs, okay? Or the amorphous cilium. Now, these are common things that the manufacturer, okay, common setups that are known, okay, at the time of these books. In some years from now, okay, which may be the time you're watching this video, there can be different combinations of these technologies, perhaps, okay? But these are the common setups, okay? And these probably will stay the common setups. And then we have another picture here, okay? So between these pictures and everything else, I think we should have a pretty good sense of digital radiography at this point, okay? Direct conversion, okay? It converts it to an electrical charge, okay? And then it's a TFT array, okay? And you can see here, the electrical charge conversion here, all right, happens at the photodiode, okay? It happens at the photodiode, and that can go to a TFT array in this technology, the CCD or the CMOS technology, right? In the indirect conversion, okay, where there's light being produced, it doesn't get converted to an electronic signal until it hits the CCD, okay? So that's some interesting, things, okay, to kind of think about this whole process of how things happen. And now we'll go ahead and we'll do a review over everything that we've learned up to this point. So here we have the X-ray production and propagation process right up here, okay? If you need a review on this, I recommend you go back to the Principles of Radiographic Exposure 1 playlist, and you can review these processes in much more depth there. All right, but the X-rays are created. The primary beam comes out of the collimator. It goes through the patient, okay? The remnant beam is what's left, and that will hit the detector. And the detector has a matrix, okay, of dells inside it, and these signals will interact with that, okay? It will interact with the capture element first, and that will either convert to light, okay, in the indirect style, and then that will be converted to an electrical signal, or it will just be converted directly to an electrical signal, depending on the technology that is used, okay, in the image plate. This signal will be processed, okay, and it will be converted to a form that the computer can understand, okay, that will be sent either with a cable, okay, with cords connected to it. A lot of them, a lot of rooms, when you put it into the bucky of some sort, it has a cable attached here, or it could be sent to through the air via Wi-Fi. This is a wavy line, so it's an electromagnetic wave, okay? That can be displayed where the operator can see it. It can be approved or rejected or whatever. It can be manipulated in different ways, and we'll talk about all those different manipulations in future videos. And then it can be sent to a network computers. Okay, and the system that we use is called PACS, Packaging, Archive, and Communication System. Okay, and that can be pulled up and looked at by other individuals. Okay, out here, we mostly work right in here, right? We mostly work all in this, right? We work with PACS too, of course. Okay, there's also the HIS-RIS systems, and there's a communication called the DICOM and other things that we'll learn about in future videos. Okay, so this is very interesting. So the whole process is there's particles, okay, electrons here, and that gets converted to an analog electromagnetic signal here, right, which is this X-rays. Okay, that goes to the detector. It's either converted into a different form of electromagnetism, which is light, okay, and then back to electrons, okay, back to particles, essentially, which is just the electrical signal, okay, or it can just go right to the electrical signal. That is then carried via a cable or another type of electromagnetic wave, Wi-Fi, okay, which is 2.4 gigahertz typically, all right, and then that can be displayed, and it can be sent to other computers, okay, and we'll learn about all those processes next. The next video will be about pre-processing and histograms. So I'll see you in the next one.